Third application. Okay, so I still have time. Third application, physics-based simulation. Now, what is that? Now, this is really before the time you born. 1997, at that year, well, when I still a student, very popular movie, Titanic. Because at that point, everybody's so excited about the movie because it looks so real at that time. Now, you can definitely try to watch the movie again. I think they released that, remake certain thing and release it again a few years ago, maybe. You can try to see whether you can find the new version online. You can try to look at the CG, computer graphic at that time. On the bottom, that's some images from Digital Domain. So that's a company doing all this sort of CG. It's a CG company. So the whole company helping the movie making industry for different scenes. And then you can also see how they make the movie, that particular 1 second shot, frame by frame. It's used computer model to try to tune the things, whether when the Titanic hits the iceberg and then split into two and then sunk into the ocean, frame by frame. And then people got to sit behind the screen and then try to tune those parameters one by one and try to make it real. Lots of time. And then when you look at that today, you will definitely laugh at it because you will feel, how come it's so fake? It's unnatural. You can easily identify that as CG. Okay, so people complain, of course, after 97, when it is a big hit to the world. Okay, and then people gradually feel, I'm not satisfied with that. And nowadays, if you're asked to pay $100 to see DiCaprio in the movie, you would definitely ask for a refund, okay? Because you are not satisfied with the technology nowadays. So people invest in the movie making and try to explore something nowadays called physics-based simulation. And this is what they got at that time. Now, what you're seeing here are from two cartoons, one from Pixar, and later it becomes a part of the Walt Disney animation. The other one is called Bout. I think they also showed it in Hong Kong that year, 2008. Were you born yet? Maybe, but anyway, you can definitely find it somewhere nowadays. So Disney Plus may got that, I don't know. But anyway, so 2001, okay, so shortly after Titanic, so Pixar came out, and then they it was such an amazing cartoon or animation, not only because the thing looks so real. Now you can see a very simple demo. You can see the motions of that big furry monster, and then it looks so real. The motion looks so real, and then at the same time, every hair you see on the body is modeled. The motion is modeled by one set of equation. Okay, so I think this is probably not the first time Pixar used math or do this physics-based simulation, but then it was such a big impact to the world, because you will feel that how come it looks so real? Because the reason why it looks so real, because there are real mathematics. There's a real physics model behind. There's a mathematical model, even though it's so big, not only 100 by 100 matrix, but then millions by millions. No one will be able to solve it by hand, but then it just simply asks the computer to solve all this mathematical problems, and then eventually give you a very realistic motion. Second reason why this is so great is that once you develop that computer software, once you generate certain scene, the director might say, well, no, it was raining outside and the hair got to be a little bit more stuck together as a patch, and it cannot be that fluffy. Okay, in old days, the artist got to go back and spend months and then redraw it frame by frame and then tune the parameter in the Titanic one by one. It's horrible. It's very difficult to make it real. But nowadays, if you already develop a computer software, all you have to do is to change a very small set of parameter, okay? And then sit back, relax, drink a coffee, and then maybe go somewhere else, have lunch, and then come back and see the numerical result on the computer. It's the same thing for the bout. At that time, they developed a mathematical model for solving a different problem. In that animation, a hamster, okay, so a hamster you see on the top, a hamster got stuck in a metal ball, in a glass ball, and then probably near the end of that cartoon, the glass ball broke into pieces, okay? The way how the crack propagate on the surface was actually modeled by a set of mathematical equations, okay? So complicated that they are not able to solve it by hand, but they got to develop the computer program to obtain an approximation to that mathematical equation. And eventually, the technology was published in a very famous conference. Okay, so it's by several researcher. So from UCLA, I did my PhD over there, so that's why I know those guys. Was some of those people, and I know how they contribute to the movie making industry. Oops, hey, how come? Okay, now more recently, another one very popular. It's Frozen. Okay, I got certain clips from the web. You can also found them on YouTube. They are demonstrating the effect of the power of their computer software. You see, all those simulations are so real, and they can make different situations, especially on the bottom. You can see that all they have to do is just to change some parameter, and then you see the snow or the ice behave completely differently. It could be because of the temperature. Okay, so it could be because it's in the daytime when there's a sun, so the snow or the ice should be a little bit watery, rather than it looks like a very solid, like in the dark when it's very cold. So you see the snow behaves differently, and that can be done very easily on the computer. Once again, just tune a very small set of parameter, then you will be able to make the movie automatically. So the overall flow for this approach is, first, you write down the mathematical equation. Usually, those equations are well developed by people in old days. When there's no computer, they might write down the equations like the Navier-Stokes equation. We saw some applications earlier, Titanic, when you see the ocean surface, the wave is governed by some wave equations, or maybe they got to solve the Navier-Stokes equation, or maybe because when you look at the snow or the texture of the muscle, then there are well-developed mathematical equations or physics equations to model those things. But those equations are in general very difficult to solve by hand, or even impossible, because they are what we call nonlinear equation and very difficult to get an analytic or exact solution. So that's why computational math can play a role. It can provide you an approximation. Okay, so it can provide you an approximation. I mentioned about Navier-Stokes equation, and here are some applications about water, fluid. All of those are from computer. They are not real, even though, well, you can look at the one on the top left corner. It looks so real. So it got interaction with several things. So that it got a liquid phase, okay? It got a solid phase, so the lighthouse. It also got the gas phase, so the air. So it's a very complicated equation involving three phase. So it's called multi-phase flow. The interactions between different things make it very difficult to obtain certain equation. And so people develop computer software to obtain different approximation. So all you are seeing on this page are from the computer trying to solve the Navier-Stokes equations or some related equations and get the solution. Okay. I mentioned about Pixar. Pixar is actually a research company. It's not like just a cartoon animation company, but it's a research company. Each different Pixar movie, they have developed a different type of technology. I mentioned about Monster Inc. earlier. So you see Fluffy. They develop a technology for hair motion. Pixar in the Finding Nemo. So I tried to find this screen from the web. They try to develop software to model the ocean wave. Okay, so on the surface of the ocean, I think this is a scene you see from, I think Nemo got caught by another dentist, right? So there's a scene shooting out from that window in Sydney. Then you will see the ocean. Okay, and then they developed a program to try to simulate the motions of that ocean surface when how the wave propagates and try to make it real. So it's once again, they develop different mathematical model to try to do different types of simulation to make their cartoon or animation look real. Okay, so Disney Picture or Disney animation try to take the same history. I think they bought Pixar years ago, and then they keep the history, and then a little bit more reason. So that's a Moana. They remake the ocean surface. So at that time, you look at the clip on the bottom, so it looks so real. It's not from real thing, but then instead it's simply from a computer. So technology improves over time, and then everything makes even more real. There's questions. Brian, is technology also used in some game like NBA? Okay, so I think there are different technology over there. Well, I'm not those PS4 too complicated. PS2 complicated for me. I only play Pokemon Go on my cell phone. I don't really know how it looks like, but then there are technology simulate. So technology itself, it's very close to mathematics. I think well, PS4 is in fact a supercomputer. I think at one point, well, maybe US, I don't recall, they limit the export of PS4 or 5 to some countries years ago because of the computational power. Like mathematicians nowadays, some of us use GPU for computation. Probably not the same technology, not the same mathematical model used on PS4, but then the technology itself, I'm sure PS4 is nothing but just a matrix processor. Okay, so if people are able to convert the mathematical equation into a matrix problem, then definitely we can use a PS4 to do our own research. Okay, but whether PS4 itself, I don't know. Maybe I can definitely try to investigate a little bit in the future. Okay. Now, earlier I mentioned that mathematicians, well, there's no Nobel Prize for in mathematics, so that's too bad. So that's why we try to explore different places and get different prize. This is another example. Okay. Now, we mathematicians try to get Oscar. Not the best actor, best actress, but if you notice, there is also a technical prize in Oscar. Let's see, 2007, 2014, the scientific and technical awards went to two groups of people. If you notice, there's one name appeared twice. That's Ron Facue. Ron Facue here. So he's actually a professor from Stanford in the computer science department, but he actually got a math PhD degree. So he is actually a mathematician. And his contributions was to develop software to make movies. And one example, it's from The Day After Tomorrow, 2004. So that's 18 years ago. Too bad you are probably before you're born. But anyway, you can still try to watch that movie. So in one scene, the snow melt down and all the water flooded into New York City. And that's a scene you see here. Because of the contributions, Oscar actually awarded him and some of his collaborators this Oscar Prize. So it was such a big news to the scientific community, especially among the computational mathematicians. We are not only getting the Nobel Prize in other fields, but then we can also get the Oscar. So that's very interesting. I see some other questions on the chat box. How about the CGI in Facebook metaverse? There are okay. So there are actually many technology in those metaverse. Even AI itself is nothing but a math problem. Okay, so I'll be teaching a multi-variable calculus course in the next semester using the AI technology as an example. There are lots of AI technology involved math. And in fact, I will try to introduce the multi-variable calculus based on something called SVM, okay, support vector machine. So that's one of the machine learning algorithm. And that's, once again, based on a very simple math model. But in order to understand that, then you will need some multivariable calculus technique. So there are different types of technology used, not only Facebook metaverse, but then when we talk about AI, what is AI? AI is nothing but just a math problem. Okay, so you just formulate that as a math problem and then solve it using. And what the technology, the algorithm itself does not need to be very fancy. Okay, like the support vector machine. Well, if you have a second year university calculus, that's multivariable calculus, and you can understand. Okay, so it basically it's the computational power that make it possible. Apparently, we are not able to wait for a really long time to get the simulation from that metaverse or some other AI application. We want real time or close to real time, and that's computational power. But before you talk about computational power, you need certain mathematical model or certain mathematical algorithm to be able to handle that problem. Okay, so that's an important importance of math. You use that, once again, you use that every day, but you might not know. Okay, okay, great. I still have a few minutes left. I was trying to do a demo, but no. So the demo I was trying to do, very simple. I try to make it real. Like, how about let's try to model how to make a movie, like modeling the spread of the oil pollutants on the ocean surface. Simple enough. Okay, so there's some oil leak somewhere. It happens in real life. One example was taken here. Oil leak in the Gulf of Mexico. I don't know, maybe 20, 30 years ago in the Gulf of Mexico. So oil leak from that and then pollutes the oceans. And then you see the oil leaks from the bottom under ocean, and then it spread everywhere. And then another example, Fukushima nuclear plant. Okay, so 311. The tsunami hit the nuclear plant, and then the nuclear polluted water spread over the ocean. Okay, so even though it's not the ocean surface, but then what we try to do here is to see whether it is possible to do a similar simulation based on certain motions of the ocean surface. there is a well-developed mathematical model, assuming that the ocean surface got certain velocity given by a stream function. Okay, so there's a field in fluid mechanics when you talk about two-dimensional incompressible flow. You can write it down as in a very compact way by introducing what we call stream functions, and then from that you can derive the velocity field. You can see that there's a parameter epsilon in the velocity field, and that makes the small variations on the right-hand side, right? You see the little vector. Okay, so the vector, we call it a vector field. It's like the directions of the wind blows. Okay, so we see the weather forecast, we see those tiny little arrow. You see the small oscillations, and the magnitude of those oscillations will be controlled by the epsilon parameter. So 0 means there's no oscillation. You see the trajectory, the motions of the oil particle or the particles seem to be very regular. But then even if you just introduce a very small perturbation in the velocity field, then you will see the trajectory seems to be very unpredictable. Okay, so we would like to use this velocity field to model the evolutions of the pollutions on the ocean surface. Okay, so that's the mathematical model. Very simple. It's just velocity is the derivatives of the position. Okay, so right, so that's the way how we define velocity. What is velocity? Is a derivative of the position. Okay, so that's probably, I don't know whether you classify this as physics or mathematics. Okay, but you surely learned that in calculus, if you had calculus, when you want to know what is differentiation. Okay, so this is one example. Assuming the boundary, so we just look at the boundary of that oil patch, and then we try to identify some points on it, and then we evolve those points, and then that would give us certain regions that bounds all those oil particles. Okay, so very simple. We are given certain initial location, we call it x naught, and then we try to solve this differential equation. So this is an equation. Given u, we try to determine this function of time, positions as a function of time. And then we try to plot the position, the collections of all this position at different time, and that would tell us where that oil patch goes. Okay, so as simple as that. But the challenge here is that we have to represent the interface. Okay, so the representations of the boundary itself is also a mathematical problem. What you are seeing here is the evolutions of certain shape in time. So this relates to the gas bubble moving in the fluid I mentioned earlier. So one gas bubble can split into more than one, and several gas bubbles can merge together into big one. So then how do you represent the surface, the interface of those things? Could be a challenging task, okay? Especially when you try to connect the points on the surface. If you have a surface, usually we use triangle to cover it. That's what you are seeing here. So that problem is called triangulation. So we need, that's also what you're seeing here. So you see the surface is covered by triangles. When several gas bubbles merge together or one gas bubble split into others, we might need to reconnect all those triangles, and it makes it so difficult in high dimension. That's some research problem. But for us, for this simulation, this demo, it's easy because we just have a curve. And we just identify a certain point, and then we connect them together. That's our surface. So that's relatively easy. I was planning to do a demo, but too bad, I don't have time. The code is not too long, pretty much 49. So 40, 50 lines of MATLAB code. Okay, so well, if we got chance in the future, then I'll do it for you. But then this is what I would get after some time. Okay, so we can do the simulation. A little bit artistic effect, so I feel the color, and then I can also make a movie. MATLAB can generate that. So you see a little patch of oil. Okay, after some time, because of the perturbations of the velocity field, then it will unevenly spread, and then start to cover a lot of regions in the computational domain, So we can do it on a computer, and then it seems that it's very natural, at least to me. It seems to model what's happening in the world. Well, of course, there are things you can change. For example, you can still change the perturbation, the epsilon, right? I mentioned about the parameter that relates to the perturbations that you introduce in the velocity field. How much oscillations that you would like to introduce? Probably you can use that to model the strength of the wind. So the wind will blow the ocean surface, and then that will change and perturb the velocity. Probably because of the temperature. The temperature can also change the velocity of the ocean. So there are lots of parameters, lots of things you can model based on that very simple parameter. Okay, so too bad I don't have time to go over the code. But before I end, I want to talk about some more real life applications. I think those applications I mentioned might not be real life enough. Okay, so you will say, oh, it's only from the movie. I don't watch a cartoon. Okay, so I don't play PS4, so I had nothing to do with those. But there are some very important applications of some related computational problem. CFD. One applications, when you go to a very big scale, you can definitely use the technology for aircraft design. Okay, so I think that's actually one of the applications interests my computational math. That's one reason why I do math. Okay, I want to do applied math. Even though in a later time in my own research, I never tried to do all this sort of research, but that's actually one motivation. You can use the same equation, Navier-Stokes equation, not only try to model the motions of water, fluid, but then gas itself, we can still use the same set of equation to model the phenomena. On the right-hand side, you see a program, a similar organized by our IAS. You know our IAS. So if you get a chance to visit our campus, try to visit our IAS. So it's on the top of the hill. When you from the main academic building, you walk past the business school and then go all the way up. So there's a very nice building. So that's our IAS. Years ago, they organized a workshop called Bio-Inspired Flight System. So it also tried to develop some flight system or autonomous system that stimulate. The idea would come from insects or some other flying birds and things like that. So they try to design the object of a flying vehicle so that it can, for example, minimize the energy, okay, maximize the lift, and etc. So those, once again, those would be an application, very important applications of CFD, computational fluid dynamics, and then people actually got some very interesting research results over there. But when was that? I think this 2000. I don't see it here, but probably around 20 years ago. Okay, too bad. So another application, weather forecast. Okay, weather forecast itself is also a CFD problem. This is from one of our colleagues in the math department. So he is doing research with the observatory. At that year, he tried to, so right here, so 2013, he tried to use a CFD model to explain the reason why the air quality at that time was so bad. It was because somewhere far away got a mountain fire, and those smokes follows the wind and then blow to Hong Kong. So that was an application, very daily life applications of computational math. And then on the left, they also study using CFD model the motions of the air. Because every time when the constructor want to build something, especially really tall building, then they have to got some report saying how much those buildings affect the air quality in that region. And those companies actually use CFD techniques, software to try to do those type of simulations and try to explain what would happen if I have certain building and obstacles in the region. That's another very important application. Now, if you want to learn all those math, the math department actually cover lots of topics I mentioned. Some very important courses, including numerical analysis, fluid dynamics, image processing. I'm actually also teaching this introduction to mathematics of image processing. And then there's a course on numerical methods for PDEs. And then there is a course on statistical machine learning. All those courses, you see, game theory, biology, mathematical biology, optimization, all those things are math. You might not see the immediate impact on those in your daily life. I don't think you need math to go supermarket, but then when you're shopping, the whole experience, there are lots of mathematics involved that you are not really sure. You browse the web, where every second when you're watching the screen, there is image processing. So the whole point here is that you might not know, but then all this math appears in our daily life everywhere. Okay, it's really everywhere. If you are curious about how people solve that problem in real life, then you will definitely need the language to understand the problem. And the language everybody uses is a universal language. It's math. Okay, so math is a language that everybody needs to pick up if you really care about and try to understand what's behind the technology, the science. If you do not have enough math, then it will be very difficult to even describe the observation. Okay, well, math is a universal language that everybody can communicate. Okay, so it's not like the English, Chinese, or other type of language that you need to spend some time. And then once you pick it up, you can only communicate with certain group of people. But then math, I think, is universal, not only limited to within the math community, but then once you got the techniques, once you got the skills, especially computational skill, then you will be able to talk to different people and try to solve different types of problems. Okay, so for that, maybe let me stop it here. In case if you got any questions, feel free to send me a message, and then I'll try to answer that if you can still stay around for a few minutes. Otherwise, I would just stop it here. Any questions from anyone? Yeah, I noticed that there's no math course in this summer institute, so that's too bad. Yeah, maybe I can try to ask the math department and see what we can do in the future, but it's too bad we don't have any math course. I think it's important to pick up some non-exam oriented math as secondary school students, if you still have time. Okay, I understand many of you might need time to prepare for the exam and etc. Any okay, so I see a chat message. What's that? Curious on the multivariable calculus. So what is the question? Now, if you are interested in learning multivariable calculus, well, not only multivariable calculus, but I'm sure there are lots of available resources online. YouTube is a very good channel. I know there are lots of different channels on YouTube teaching people math. There is a MIT open course, especially for calculus and multivariable calculus, and there are well-developed learning materials online. So I think they are very user-friendly. Even you are not studying at the university yet, but then you can still pick up those materials. But if you know, but what is multivariable calculus? For the typical high school calculus, the function is just a function of one single variable. When you see function is an f of x. But then there are functions involve more than one variable. So that's a f of x, y, and then that it could be t corresponding to time. So when we have functions with more than one variable, how can we generalize the definitions and the skills that we learn in single variable calculus to functions with more than one variable? First, we have to generalize all the concepts, including limit, differentiation. So what is limit if we have functions of more than one variable? When we talk about differentiation, well, what is the differentiation if f is not only functions of x? Okay, well, in the formal definition, we got f of x plus h minus f of x, and the whole thing divided by h, and then take limit h equal to 0. But when f involves more than one variable, how can we do those types of things? So we need the formal definitions of generalizing those things. And then it turns out there will be more than one type of derivatives. When we talk about integral, so what sort of integral that we are talking about when functions got more than one variables, right? So instead of function defined on a real line, we have a function defined in a space on a surface. In those cases, then how can we define integrations over those sort of domains? So that those will be the topic we discuss in multivariable calculus. Okay, so basically it's a study of functions with more than one variable, generalizing the concepts of typical calculus to functions of more than one variable. Okay, so that's a very general introduction of multivariable calculus. Okay, so I guess I have to stop. It's 5:07 already, so I don't want to keep you here for too long. Once again, too bad I don't have time to go over the demo. I really want to show you the demos, showing you the importance of coding. So you might not be interested in doing a math degree, but even computer science, I know AI is so popular. So how to use computer to solve some simulations, I guess it's good to do some demonstration for you so that I can still motivate you guys to do a STEM degree. So, but anyway, so in case we got chance in the future, I'll do it later. Okay, so thanks a lot for staying until this point, and I hope you enjoyed the talk. Hope to see you again later on our campus. Okay, so a little bit recruitment advertisement. Okay, so let me stop here. Bye-bye.